Before we press on into MA, I want to review kVp, further define some things, and introduce quality control, because every aspect of our beam and how we control the beam has to be accurate. So we have to test it periodically to make sure that the kVp that we set is the kVp that we create, the MA that we set is the MA that we create. The time that we set is the length of time the exposure is made, and so forth. So just to review kVp and what it controls in both the X-ray tube and throughout the circuit and in the beam itself, the kVp is what we call potential energy. It's electric potential, and it's the potential difference across the X-ray tube. Again, it's not created until we get to the point of exposure. So whenever you're rotored, you're not applying kVp and you're not creating X-rays. X-rays are only created whenever kVp is present and the electrons travel across the tube. So during prep, you have no kVp applied to the X-ray tube. It's just filament circuit, filament current through the filament itself. When we press the exposure button, that's when we apply the kVp and the electrons jump across the tube. So now we've truly got tube current whenever we apply the kVp. The kVp increases the positive charge and increases the negative charge across the tube so that the electrons become more attractive to the anode, and they'll make that travel across. And whenever you increase your kVp, let's say you set 50 kVp, the attractiveness is specific to that 50 kVp, and the electrons travel across the tube, and they're going to travel very, very fast, but not as fast as if you increase your kVp to 100 kVp. So in that way, kVp controls your potential energy. Potential energy controls the kinetic energy. So as you increase your kVp, you actually increase the speed with which the electrons travel across the tube. They carry more kinetic energy with them. As they carry more kinetic energy, they have more kinetic energy to lose. And with that increase in kinetic energy to lose, we can get a higher kVp X-ray photon, because the creation of the X-rays are, especially in the BRIMS X-rays, are all about loss of energy. So more energy to lose means that we can create an X-ray beam in an energy range that's higher because we've got more energy to lose. So again, it controls potential energy, which controls kinetic energy, which controls the speed of the electrons. But once we get to the photons, they all travel at the same speed, that being the speed of light. So the difference is in the frequency and wavelength of the individual photons. So a 50 kVp peak energy X-ray photon is going to be of longer wavelength than a 100 kVp X-ray photon. A 100 kVp photon is going to be shorter wavelength. So the 100 kVp is going to have a higher frequency because you can fit more of those waves into a given space than what you can with 50 kVp. So the 50 kVp is going to be of lower frequency. In the BRIMS spectrum, it controls directly the peak energy that you create, but if you remember, secondarily, it controls the numbers, and it really controls the numbers exponentially. So you're going to have a difficult time with the understanding that kVp doesn't control numbers. Well, it does. It does control numbers, much more so than what mass does, but it's not what we use to control numbers. And in that way, we say that mass is what we use to control numbers, and therefore mass controls numbers. All right. So it controls the peak energy, it controls the average energy, and it controls secondarily the number of photons that we create. Now, I've spoken quite a bit about kVp and beam quality, And beam quality is what we use to control beam quality. But if you remember back to last semester, we talked about beam quality as that kVp is not the definitive measure of beam quality, and it's not. Because beam quality, high quality X-ray beam, if you remember, it takes into consideration much more than just kVp. So if you have kVp, a high kVp X-ray beam, but almost none of the peak energies are represented, even though they're there, there's almost none of them, then you have a certain quality. But if you have a second X-ray beam where almost all of the photons are those peak energy photons, then your quality is totally different. The second example there would be an extremely high quality X-ray beam. Even though they both have the same kVp, the second example would be a very high quality X-ray beam, as opposed to the first one would be low quality. So peak energy is not the only thing that controls quality. Quality is also controlled by average. So if you think about the different things that control the average and affect the average, you've got kVp, you've got machine phase, and you've got filtration. So taking all that into consideration, what the best measure of beam quality is half value layer. And again, I'd refer you back to last semester where we talked about half value layer. If you have two X-ray beams and you set the same technique on both of those machines, and you make an exposure, let's say at the same kVp, maybe 80 kVp, and your exposure shows that after you shoot through a layer of some sort of absorber, and before that absorber, maybe you have 50 milliroentgens worth of exposure, but after it, on the first X-ray beam, you have 25 MR worth of exposure. Then that absorber cut that X-ray beam, the quantity of radiation in that X-ray beam in half. That's what you call a half value layer. A half value layer is the amount of an absorber required to reduce the intensity of an X-ray beam to half of its original value. Original value is 50, went through the half value layer, cut it down to 25, you got a half value layer. So we would say of that X-ray beam, the first X-ray beam, that one half value layer, or one unit of whatever absorber we used, usually millimeters of aluminum, would be its half value layer. So 1 millimeter of aluminum would be that first X-ray beam's half value layer. So if we made an exposure in a different room and the technique was the same, kVp was the same, mass was the same, and we made the exposure on the same half value layer, but instead of cutting it from 50 to 25, it cut it from 50 to 40, then what we've got is significantly more radiation after the absorber in the second room than what we had in the first room. And since we have more penetration, since we have more penetration and remnant beam in that second room, then we can say that that X-ray beam is of a higher quality than the first one. So what it might take in order to cut it down to 25 is it might take 2 or even 3 half value layers. So that half value layer, the amount of absorber that it takes to cut your beam in half when comparing two rooms, whichever room has the higher number in half value layers, 3 millimeters of aluminum, that beam is going to be much more, or a much higher quality X-ray beam than the X-ray beam where you only have 1 millimeter of aluminum as its half value layer. So beam quality is is a product of all those other things, and the overall beam quality in an X-ray room is going to change over time because of the added inherent filtration because of the tanning of the tube. So I'll take a little bit of a diversion here and talk about quality control. Since we set a kVp and we set a mass and we make an exposure based on that, and since we get the tanning of the X-ray tube, the tanning of the X-ray tube adds inherent filtration, which reduces the intensity of the emitted X-ray beam. So over time, what we're going to have is a lower output in a given room. The kVp may remain the same, but what we'll have is a reduction in output. So we have to go back into the machine and we have to make adjustments to make sure that the output in kVp and mass remains constant throughout the life of the X-ray tube. So we don't do that, but a physicist will come in periodically and take care of that stuff. The physicist will run a lot of quality control tests. He'll test kVp, he'll test MA stations, he'll test time, he'll test reciprocity, which is same mass values with different MA and time. He'll test focal spot size, he'll test collimators, he'll test how perpendicular the beam is. There's a number of different things that he's going to test at least once a year to make sure everything's shooting right. kVp it's possible for kVp to get off, and in some cases what causes the difference between what you set and what you actually get is that the motor that drives those contacts on the secondary side of the auto transformer may slip, or you may have some sort of bad connection on the secondary side that causes you to get a different kVp than what you actually set. So all these QA tests have to be conducted at the same time. And kVp, what they do is they come in and they make an exposure on a ionization chamber, or a device that in a lot of cases does a lot of different things. It's an ionization chamber that can measure kVp, and it can measure MR per MAS output and a lot of different things. But they make an exposure on this thing, and it tells them exactly what the kVp was. They shoot it with the X-ray beam, and it tells them exactly what the kVp was. So they can compare what it is that they had set to what it is that came out of the machine, and if there's a difference there, then we have to call somebody to come in and manipulate the machine and get it shooting properly again. So the difference between what your machine puts out and what you have set has to be within plus or minus 5%. So some of your textbooks are going to say different things. Some will say 3 to 4 kVp, some will say 6 kVp. And when there's differences, then you need to consider a couple of different things. If there's differences between textbook authors, chances are they're not going to be that specific on the registry. But what you need to look at are things like what the industry standard is. Like here, this is a publication that references kVp and the accuracy of kVp. It needs to be less than plus or minus 5%. Okay. So that's according to the IEC 61676, which is at the IEC website here. And IEC stands for International Electrotechnical Commission, or something like that. So it's it may not be the authority, but it's an authority on how well things should operate as far as electrotechnical machinery should work. So in this case, it should be plus minus 5%. So if we think back to what we talked about before in kVp and how much of a change that it requires in kVp to make a visible difference, that 5% can make a visible difference on your image. But now you consider what your baseline is for when to repeat an exam because of inadequate exposure. And really, yesterday whenever I recorded the rest of this, the previous slides on this, I said that the 5% is similar to 30% on mass. So if you underexpose a patient by 30%, it's really not worth repeating. Or if you overexpose somebody by 30%, or if you underexpose a patient, then a 30% change is not enough to affect a really good difference. That's your baseline for how to see a visible difference. Generally speaking, if you underexpose a patient by enough that it needs to be repeated, then you need to double your mass. So carrying that forward into kVp, if we underexpose a patient by about 5% being about a third of 15%, 15% is what's required to double your exposure, 5% is really not all that much. It sounds like it is, really not all that much. So what are the effects of kVp on contrast? As kVp increases, we get more penetration through the patient. That gives us less differential absorption. More tissues are penetrated equally, so the contrast goes down. The effects on dose, make sure that you pay attention to your test question. If the test question asks you for changes in dose, this is patient dose, changes in patient dose as kVp goes up, and that's the only thing it asks for, don't apply a mass change to it. As kVp goes up, if nothing else changes, then your patient dose likewise goes up drastically. If kVp goes up and you compensate with a change in mass, in other words, if you increase your kVp by 15% and you cut your mass in half, your patient dose goes down. If you decrease your kVp, and that's the only thing that you do, then patient dose goes down. If you decrease your kVp and increase your mass, decrease your kVp by 15% and double your mass, then your patient dose is going to go up. So what do we get? Well, as we increase kVp, we're going to increase grayscale, increase latitude, decrease contrast, increase patient dose. So now the effects on the image receptor, we got to consider that as well. So the same thing is going to happen as we increase patient dose. The same thing's going to happen with image receptor exposure, in as much as when we change kVp only. What I mean by that is if you increase kVp and you don't do anything else, then patient dose goes up, image receptor dose goes up. If you decrease kVp, patient dose goes down, image receptor goes down. If you increase kVp by 15% and cut your mass in half, patient dose goes down, image receptor exposure remains the same. So the 15% rule is, does a couple of things. One is it changes the patient dose while maintaining image receptor exposure. If you decrease your kVp by 15% and increase your mass, double your mass, then your patient dose goes up, your image receptor exposure remains the same. So the 15% rule, which is a change in kVp by 15% and an accompanying opposite change in mass by a factor of 2, is to maintain image receptor exposure. Some of your test questions are going to get complicated. I know you find that to be surprising. So pay attention to what the test question is asking you. When you change your kVp, what are the effects on patient dose? What are the effects on image receptor exposure? So you may have a question that asks, as you increase your kVp by 15%, what happens to image receptor exposure, what happens to patient exposure. But you may have questions that give you hypotheticals, saying something to the effect that you made an exposure and you needed to change your image receptor exposure on a repeat by 100% using kVp. What would you do? Well, you'd increase your kVp by 15%. You may have one that says that you need to increase your image receptor exposure by 200%. What do? Well, you increase by 15% twice. It may ask you what you would do if you needed to affect a change in grayscale. You might need a longer grayscale and have the same image receptor exposure. What would you do? That's your 15% rule. You'd increase your kVp by 15%, you'd reduce your mass by a factor of 2. You may have a question that asks you, that tells you that you need to lengthen your grayscale and cut image receptor exposure in half. So what would you do there? Well, 15% rule, increasing kVp by 15% and reducing your mass maintains the image receptor exposure. So in this case, what you would have to do is increase your kVp, reduce your mass to get back to your original image receptor exposure, and then reduce your mass again. So it would be increase your kVp by 15%, cut your mass in half, cut your mass in half a second time. So the questions may seem complicated, but if you take them one step at a time and consider and understand what the question is asking you, and then take those steps one step at a time instead of letting the entire question overwhelm you, I think you'll have an easier time with them.